Okay, we're starting chapter 2, and it talks about discrete inputs and outputs. So when I go and I take a switch on the wall, and I go and turn it off, that's discrete. It's not continuous. It can only do one thing. It can be on, it can be off. So that's the only thing it can do. Because I might have three-phase power, I may have to have something that turns on and off all three phases at the same time. So I could do that. So I could have a normally open switch ganged together that turns on all three phases at the same time. A, B, C. I have a switch has something called a pole. That just means I have, if I have one pole, that means I have one way for power to go through the switch. If I have two poles, that means I have two ways for power to go through the switch. Two poles. If I have three poles, that means I have three ways for power to go through the switch. In general, when the poles will be different phases, different something. So I'd have A, B, C phase going through there if I had AC power going through the switch. I have an A side and a B side of my switch. My A side is away from power, my B side has power coming to it. So I normally have power coming into the part that's coming open, and the part that isn't, I don't, when I close it, I have power going to it. On page 28, we have toggle switches, push button switches, rocker, slide, rotary, key, and dip switches, among other things. They could be a snap action switch, or they could be a mercury switch. So the switches on the back that control the lights, those are mercury switch. I can feel the mercury going back and forth. So what we do is we go and, instead of having a switch that is mechanical, we have something with mercury in it, and then that the mercury will make contact. When it's tilted one way, I'm open, so my mercury sits there and I don't have any contact. When I tilt it the other way, my mercury is sitting like that, and I end up with contact. Mercury is a nice conductor of electricity. It works quite well. As a contaminant, it is really bad news. So we have to put up with those things. But it's nice to play with. Just don't eat it. Don't put it in your hair. Don't do things like that with it. Okay, I'm looking at page 28, and I see I have switches that could be both normally open and normally closed. So I've got a normally closed part of the switch, and I have a normally open part of the switch. I have power, voltage coming in on one side, and I'm going to something going to the other side. I could have them in multiple, ganged multiple ways. Page 28 shows a nice picture of how I do that mechanically on the inside when I throw the toggle. We would call this single pole, because I only have one phase of power going in, but I'm double throw. So I can be either shut that way or shut that way. That makes it double. Single.
Double throw?
Yeah. Single pole, because I only have one source of power, but I'm double throw. I can spell throw. Is there a T at the end of throw? Oh well. On the same page, I have double pole, double throw switches, and triple pole, double throw switches. So I can buy whatever I want to buy in the switch. I'm sure somebody makes it for me. So on page 30, I see that I have some DC power, 28 volts DC. Going into a set of running lights. So I got a red light, and I've got a green light. Oh, I got a green light. Those guys are hooked up to ground. And then I got another circuit that has AC power hooked onto it. And those two switches are hooked together. So one of the poles of the switch is taking 28 volts DC, and the other pole is taking 120 volts AC. And we're turning on some motor. Maybe we're turning on some motor. There, now we're turning on some motor. But I had 28 volts going to my indicating lights saying that I'm off or I'm on, and then I know that my motor is running. Do we like this circuit a whole lot? No, because the switch could be shut, the green light could be on, and the motor could have burned out 10 years ago and not be running, right? So it's sort of like a circuit that if the green light is on saying the motor is running, then the motor should actually be running. That'd be something that you'd sort of like to have in a circuit, right? And this particular circuit doesn't do that. On page 31, we do the same thing, but now we have a push button. So we have a push button switch, and we have the normally closed side of the push button going to 28 volts DC, going to my running light, my off light, red. And then I got my 120 volts AC going to some motor. And then I push the button, it disconnects from the red, it touches down here, and the motor turns on. This is called a make before break circuit. No, it's not. This is a break before make circuit, right? Is that what I said? Now, when I close a switch, so I've got a switch and I'm going to close it. I got 120 volts over here. I expect that I'm at 0, and when I close the switch at some time, I'm going to go up to 120 volts, right? If I could write 120 volts, which I can't. Is that what really happens? If I go over there to the lights and I shut the switch, what happens? The lights come on. If I open the switch, the light comes off. It appears that that's what is actually happening. The problem occurs in your eyes. If I could come through that door, come sit in this chair, get out and walk through the door, and do that in 17 milliseconds. If I could do that in 17 milliseconds, no one would have seen me come in the room. Your eyes have a you have to, something has to be there that long. So if you remember in the original Star Trek when the captain got speeded up by 1,000 times and he'd go in and out of the room and do things and everybody was standing still and no one could see him. If he wanted anybody to see him, he would have had to stand in one place for a considerably long time for somebody to be able to see him. When we do our moving pictures, when we go to the show and see our pictures, what are those guys? 32 frames per second?
30 frames per second.
30 frames per second?
24.
Yeah, 24 frames per second. They look like a moving picture. It looks like continuous to us because it's happening faster than our eyes can distinguish the individual frames. And that's just, nature did that to us. So what happens when I close the switch, if I look at it for the first 10 milliseconds or so, what's actually happening is the switch is bouncing off that contact before it firmly heads there. So my voltage is gonna do something like that, and sometime around 10 milliseconds, I'm gonna be at 120 volts. So when I have circuits that inside of 10 milliseconds matters, then I'll have to do something about that situation. Right now, when I'm talking about turning on the light, do I care about inside 10 milliseconds? No, I don't care. When I turn on my car, do I care about inside 10 milliseconds? No, I don't care. So in most applications, it doesn't matter. The application where it will matter will be our program logic controllers at the end of the semester. These guys do an input scan maybe as many as 2,000 times a second. And maybe quicker than that, depending on how long your program is. Well, at 2,000 times per second, and the switch is going back and forth like that inside of 10 milliseconds, that means that in the first 2 milliseconds of time, this could see the switch going off and on several times. That may or may not be a bother. If I'm sending a quarter down a Coke machine, then that would be a bother. If the Coke machine saw 3 quarters every time I put in one. Now, it wouldn't be a bother for us who's paying for the Coke, right?
That's right.
But it would be a bother for the salesman who's trying to get a profit off this machine. It'd be a bother for the Coca-Cola company. So you have to mitigate those some circumstances. And when you think about things like an Ethernet speeds of 100 megahertz, a whole lot of things can happen inside of 10 nanoseconds that are not accustomed. So anyway, but this is chapter 2, and in chapter 2 things are off and on. If I look on page 32, I see that most of my switches are good to 10 amps, 6 amps, 2.5 amps if I'm DC. And I can take a pretty good load through those switches. So an industrial switch taking 10 amps for the whole life is a reasonable thing to do. Now, I've got this switch that's going on and off right here. How many times can it go on and off? 10? How many for 10? At least 10. At least 10. How about at least 100? How about at least 1,000? How about 10,000? When was the last time you replaced a switch anywhere in your entire life?
Huh? I can remember.
Not 6 months ago, yeah. So some of us have different lives. So in general, an industrial grade switch is guaranteed for 500,000 openings and closing. The ones you buy for your house are only good for about 100,000 openings and closings. So your bedroom light switch, you turn it on twice a day, turn it off and on twice a day, once in the morning, once in the evening. That's still considerably number 50,000 days, right? So that's many years before you have to replace it. You're probably going to sell the house to somebody else before you have to replace the switch. So that is the way that it is. Now, why does this perfectly good switch fail? Why would it do
There
that?
isn't how type works out.
But how? How's it going to wear out?
Arcing?
Yes. So a little bit of arcing across the switch every time you open and close it is going to cause a little bit of the copper to deposit on the switch someplace else. And with that depositing of the copper on the switch, there's going to be some time between now and 1,000,000 cycles of the switch where it's not going to work anymore. Now, if it's an expensive switch, you can get a piece of sandpaper the corrosion off, and it'll work again for another 500,000 cycles. If not, then you're just going to have to go and put a new one in. Now, if you have one of those mercury switches, you're not arcing and sparking anymore. And so they're going to last longer. You're going to pay more for them, they're going to last longer. Now, your AC outlets in the house, on the other hand, when was the last time you replaced one of them? A couple days ago, right? So I end up replacing all of mine every time I paint the room because they're broken. So I had a situation in my son's house in Ledyard, Connecticut. The refrigerator doesn't run. The refrigerator doesn't run. You know, you go there and you have no power.
So somebody prank called you.
So here's the refrigerator. Here's the switch. Now, in a house, the switch behind the refrigerator is dedicated to the refrigerator. It's on its own fuse, right? By code. By code, that's what it is. All right. Now, who's the idiot that inspected this guy? Anyway, I have no power there. I go down to figure out what fuse is open, and none of the circuit breakers are open, and they all have power, because you can have a circuit breaker that's open that's still shut. So there's a trip position on your circuit breaker, and you've seen that before. You have a trip-free position. You close it, you open it, you close it, you set it back up, everything's fine. But you can also have a circuit breaker, due to age, fail shut and actually be open. So, and that happened to me only 5 years ago. The furnace isn't working. The breaker's perfectly okay. By inspection, I look at it. The furnace guy shows up and replaces the breaker. The furnace now works. Yeah. And I'm the electrical engineer. You know, why didn't I put a volt? You know, for all of $2.50, I could have fixed that too. Anyway, so now we're looking to figure out why the refrigerator doesn't have power. So we look this way, and we have power above the sink. We look over here, no power. There's a door there. We look over here, no power. We look there. Now we're in the dining room, no power. We look on this guy, no power. We look over here, no power. But sometimes I do have power. So sometimes I have power, sometimes I don't, depending on where I'm putting my voltmeter. Well, that's pretty weird, you know, of all things. Well, as it turned out, the glorious electrician had ganged together 6 different guys going to the refrigerator, violating the code, of course. And this plug right here is next to the front door now, and is the most likely spot to plug in your vacuum cleaner. Now, as a group, we don't plug in vacuum cleaners, right? No, mom plugs in the vacuum cleaner, the daughter plugs in the vacuum cleaner, the wife plugs in general. And we're not the group that unplugs the vacuum cleaner either, right? So in general, it just plugged in, stays plugged in until we trip over it, right? Right. So, but because it's the plug that's used all the time, it was broken. And they're ganged together.
Oh, so.
Yeah, and they're ganged together, and so I of course replaced this guy first. Didn't have any effect. Then I went back and I replaced that guy. But physically broken AC plugs need to be replaced before they cause you. They're not going to burn the house down. They're just going to turn power off to whatever it is you're using. Okay. On our submarines, it was about every 10 years is all they'd last. The atmospheric conditions of submarines in the 50s, 60s, and 70s was such that that's how long the plastic lasted. And we're constantly replacing them underway. In our newer submarines, where we have much better atmospheric control, we probably never replace an AC plug. The electricians probably don't even know where the spares are, because and that has to do with CO2. So, in the up to about 95 or so, normal underway conditions on a submarine had CO2 about 0.09% of the atmosphere. And normal for human beings is that. So nine times normal would be the normal on the submarine. You could get it down by going up and snorkeling, but we're in the middle of the Cold War, so we didn't do that. After the Cold War ended, we changed our rules, and we snorkeled for an hour every week, or whether we needed to or not. And then we built then we went and secured the smoking lamp, and so we don't smoke on our submarines anymore. And then we put in better scrubbers. Now, the newer class submarines get it all the way down to there's no difference in the CO2 level underway on a submarine or not. Now, the medical consequences are unknown of that increased thing, but there is the normal birth rate of males and females in the United States is like 102 females to every 100 males. So that's the normal birth rate. In the submarine force, we normally have girls. So I have a lot of friends that have 2 or 3 girls, no boys. And we think that was caused by the CO2, but we're not sure. It turns out that after war, we normally, like World War II or World War I, the birth rate shifts and we get more boys to have more males in the population. And it's a biological thing going back hundreds of thousands of years. So it might just be that it's what we're doing. We don't want our sons to be submariners, therefore we don't have any type thing. That could be it too. Just one of those funny things, you know. There's every now and then. What's the purpose of science? Anybody know? Yeah, to understand more. So, if I look at science as it existed 500 years ago, and then I look at science as it existed now, we would see that maybe 5% of what was there 500 years ago is still true, right? But a whole lot of the stuff that was there 500 years ago isn't true anymore. So a mere 140 years ago, my great-grandfather knew the earth was flat. He was a farmer in Michigan. He could stand on his farm, and he knew the earth was flat. There's no telling him otherwise. Well, if we look 500 years in the future, how much of the things that we know to be totally and 100% true today do you think will be?
5%.
Yeah, maybe 5%. So that's an interesting thing, right? So we scientists tell us something. Anyway, the scientists have found a quasar that's 4 billion light years across. Now, the universe itself is only supposed to be 14 billion light years old. And one of the tenets, one of the rules of our physics as we currently understand it, says that the universe is uniformly distributed in its matter. Okay, so if I take a big enough hunk of the universe, I'm going to have the same 4 atoms per cubic meter, even though I throw in the sun. Because by the time the sun fills up all that other stuff, it's still going to be only 4 atoms per cubic meter. so the theory that gives us the Big Bang, that set of physics that gives us the Big Bang theory, also says no object in the universe can be greater than 1.2 billion light years across. All right. Which, of course, now brings into question just about everything. Now, when you put this in perspective, our galaxy is only 100,000 light years, and from here to the next galaxy is only 2,500,000 light years away. And so something, the first thing that crossed my mind is, why did we just find it?
Yeah.
I mean, this thing is huge. How could we have missed it? You know, but it violates our current understanding of the universe. Well, that could cause significant changes in how we think about the universe now and how we think about the universe 500 years ago. And that's what we're supposed to do in science. We're supposed to make observations, adjust our theories about the nature of the truth, whatever the truth might be. This thing has black holes that are the size of our galaxy. 2 or 3 of them. Maybe more. Yeah. Pretty cool. Anyway, what does that have to do with industrial stuff? I don't know. All right, so I'm looking at page 33, and I see I have amps. I have life expectancy of an operation depending on the amount of amps I sent to the switch. So depending on the amps I sent to the switch, I have some life of the switch. And as you'd expect, it's an exponential function. And so if I'm only going to send through a mere 2 amps, then I would expect an age of 10 million cycles. 5 million cycles. We'll go with 5. We'll go with 5 million cycles. 5 million cycles on some. But if I go and send in 10 amps, then I expect only 500,000 cycles on that switch. And that has to do with the arcing and sparking caused by more amperage. So now I got this switch that switches 10,000 amps. Now, how long is it going to last? How many times can I take a switch that switches 10,000 amps and go from open and close and back the other way? And the answer is lifetime employment for us. It's not going to last very long. So there's 28 people currently in the 28 jobs that deal at OPPD that deal with switches. Because these switches, so they have automatic switches. One of your classmates goes and knocks down a pole someplace and secures power to the school. The school has alternative power. So the school has 2 sets of power lines coming in from 2 different sources. We knock down one of the poles. We switch over. Within 1 second, we're going to switch over to the alternative power. Okay. Now, why are we on one and not the other? One of the powers is cheaper than the other. That's why. So it's a matter of money. And so the sooner we can get back to the primary source of power, the better. After a car accident, it takes about an hour for the crew to get out there and fix whatever the problem is. The switch will automatically switch back to primary power. So what I do, because the machines in this room and my office don't think kindly of power surges, when the power goes away, the computers turn off, I wait for the lights to go off again and switch back to primary power before I turn my office machine back on. Okay. Now, do your houses have 2 sources of power? Why not?
Can't afford it.
Can't afford it, right. So you only have 1 source of power, and when your classmates knock down that pole and knocks down that wire, power will come back sometime. But that's the way it is. Okay, so after Hurricane Gloria, I spent 6 days in my house without electrical power, and the 7th day we ended up going to the Holiday Inn. Because we didn't have any water, we had a well. If you don't have electricity, you can't have water, and my wife filled up every container she could find with water before the hurricane got there, and we lasted 6 days before we went to a hotel on the 7th day. On the 7th day, power came back. Yes.
We're also had the generator back up to his house. Big generator that goes to his house.
Yeah. Do you have one at your house?
So my uncle does.
Yeah. When I have a house in Georgia, when I move back to Georgia, I plan on putting a backup generator there. No, I don't plan on doing it for the renters, but when I go back, I expect that to happen. You can also do little things. So you can get a 500 watt solar energy thing for about $350 at Menards, and that would be enough backup power to run your refrigerator, as long as you didn't have it open all the time. Okay, it wouldn't be enough backup power to do the rest of the house, but it'd be enough backup power to start your refrigerator and have it run. Huh?
Did you just buy another gun?
You could, yeah, but my house used 2 kilowatts per day during the summer when I was in Connecticut. My house in Nebraska used 2 kilowatts a day every day. So this is 500 kilowatts per hour. Now, what was causing that? No, the air conditioning was off. No, if the air conditioning was come on, it'd be much more than that. That was being caused by the house phone that was plugged in, a clock in the master bedroom that I didn't unplug, but I unplugged everything else, and 2 lights that were coming on, 2 fluorescent lights that were coming on for about an hour in the morning, hour in the afternoon, and the security system, whatever power it was doing. So, to power the house, that would be enough to do that. And then there was nothing in the refrigerator. The refrigerator was still on, so it was still cycling on and off too. The water softener still had power going to it, although it wasn't using anything. So you could do that, and you could buy more than one, but that's still pretty expensive at 500 watts. $350 for 500 watts. Okay, turning the page. On page 34, we have calculations of how many shifts I need to do whatever. All right, well, if we have a problem like that, we'll go back to that page. Page 35, we talk about protecting my electronic gear, my electrical gear. So in the lab equipment that we have, when we're running our wires with 3-phase power, we have type 3 type connectors. It's good for dirt falling on it, rain, snow, blowing dust, and external ice formation. It's good for those guys. But if I want to switch to be good, no matter how much how hot the fire is, then I need something different. So as I move up in NEMA, anybody know what that stands for? National Electrical Mechanical Association, maybe. As I move up, I'm good for, so type 2, I can splash liquids on it. Type 3R, I'm good for ice forming. Type 4, I'm good for a hose spraying the water down. So in an industrial setting where at the end of the shift I spray all the gear down, I would have to have type 4 equipment. Type 4X, external corrosion, flying debris. So if I want to have my switch work during a hurricane, I need a 5. Occasional submersion to limited depths. So can you imagine any of my three-phase controllers being submerged to any depth at all and still working? No, probably not. Dirt falling, whatever. So depending on the application will depend on what enclosure I want. So I'm on the moon. So here I am. I'm on the moon, and I'm building an industrial facility up here on the moon. I got my first 1,000 workers there. And the issue is, what type of enclosure do I want my switches in? And probably type 1. Is there any dirt? Is there any wind? Is there any corrosion? I mean, the worst thing that's going to happen to me is the temperature is going to change, right? As the sun comes and the sun goes. So for 15 days during the month, I'm going to be in sunlight, and for the other 15 days of the month, I'm going to be freezing. And so how do I handle that?
Put it in the enclosure.
Oh yeah, no problem. You have a railroad track going around the moon, and you put your colony on the railroad track, and you move it so that half the colony's in the sun and half of them's in the shade all the time. And that way you don't have any problems like that. Yeah. What a great idea. Yeah. Yeah, almost as great. The National Geographic this month has an article about in the 50s, the rules of engagement in the 50s were different than the rules now, right? So what we could think about and do in the 50s allowed us to go to the moon in the 70s. We haven't been back since 79. What kind of a species are we anyway? So the guys were sending them to the moon in the 70s. If they didn't come back, well, that'd be a bad thing. We'd hold a funeral, right? Now we wouldn't allow it at all. If we couldn't get them back, we wouldn't allow it at all, because our safety requirements of workers have increased. Well, we're never going to get off this planet if we don't take some risks, right? But one of the things in National Geographic is a rocket ship that goes and blows up nuclear weapons behind it to propel it forward. Okay, so we have a spaceship that looks like this, and we send nuclear pellets out here to blow up have nuclear explosions back here to push the spacecraft that way, to send it to Mars or send it to the other planets. Or today would we do that today? Yeah, probably not. But during a time when we were doing open above ground nuclear testing, this seemed like a reasonable thing to do, right? Yeah, pretty much reasonable. Yeah.
As long as you do it far away.
Yeah, exactly. And then, of course, my Death Star proposal to the White House been shot down. You heard about that, right? Yeah.
That was about the time of the Ronald Reagan with the Star Wars.
Yeah. Yeah. Well, the White House got 25,000 people signed a petition to build a Death Star, and they just wouldn't do it. How would you do such a thing? Well, there's the sun. There's Mercury, Venus, Earth, and there's Mars and Jupiter's out here. Between Mercury and Jupiter, there's an asteroid belt. What is that asteroid belt made out of?
Asteroids.
All the things that we're made out of, except it's spread out. So if you think about the iron core of the Earth, that'd be really cool to have all that iron, right? We just have an itty-bitty bit that's on the surface compared to all the iron in the Earth. Well, in the asteroid belt, all that iron is there ready for us to take. So if we could get some manufacturing facility out there in the asteroid belt, there's no reason we couldn't have enough materials to build a Death Star out there. Now, there are some issues of the nature of man, and destroying planets. That's not high on our list to do, right? So yesterday was it?
Actually, kind of
yeah. So yesterday on The Mentalist, there were two hardened murdering criminals that refused to kill a child. You know, so if we send somebody out there to blow up a planet and he refuses to kill a child and there's a child on the planet, I mean, how's that gonna work? You know, so we build a Death Star and now we can't use it because no one's gonna pull the trigger. Yeah. I know. So that's what the White House was concerned about, that we waste taxpayer money. All right, on page 36 and 37, we're talking about hazardous conditions and how that's going to change the price of what we're doing. Okay, so let's say I got jet fuel here. Is it J4? JP5. JP5. So I got a tank with JP5 on it in my aeroplane. There's my aeroplane. Okay. I guess I need something else, like wings. Yeah, there's the wings right there. All right. So how am I want to send some stuff through the tank. So should I? Yeah, I got a 120 volt line over here, and I'm going to send it through the tank to over here. What do you think?
That sounds very fun.
Am I going to send it through the tank or not? No, I'm not going to. Well, what if I went and put a pipe and sent it through the pipe in the tank? Would that be okay?
I don't think so.
You don't like that idea either?
I don't like that one.
So you don't like my wires going through the tank?
No, not at all.
Oh, bunch of, I don't know. You guys are all hard to please. Okay, well, what if I?
Hired by the FAA.
Yeah, I know. What if I go and use a fiber optic line going through the tank? Would that be okay?
That is, because that's not flammable, right? So it's just like.
Yeah. What if I just put a hunk of fiber through the line, and instead of having 120 volts, I have this fiber shut some breaker over here to turn something on.
That sounds better.
That'd be better?
I like that one.
Yeah, okay. You like that one?
It
Better?
probably costs a little more though.
So, no, it probably costs a lot less than trying to make the 120 volts work. So, anyway, that's what this is all about. You know, how do I mitigate things like that? So I got a tank of alcohol, a million gallons worth of alcohol. What am I going to do to know how much is in it? You know, going to light a match and look down the hole. You know? What am I going to do? Okay, so now we're moving on to page 38 and 39, and we have more expensive toggle switches.
Ooh.
And on the top of 38, we have a whole bunch of symbols. So I can have a resistor, and I can have a potentiometer. What's the difference between a resistor and a potentiometer?
You can adjust the resistance.
Like very little, nothing at all, right? Yeah, right. So if all I did was hook, if this were a 1K potentiometer, and I just hooked up wires there and there, I'd have a 1K resistor. It's only when I go to the wiper in between that I can vary what I'm doing. And then I have capacitors, inductors, conductors. Oh, there we go. There's a conductor. Batteries. Plus on that side, minus on that side. Fuses. And normally open, normally closed contacts. Now, we have electrical symbols and we have industrial symbols. Now, why? Why did you do that to me? You know. So
Why?
Why ask why? That's what you really want to know.
Mm-hmm.
Yeah. So the industrial symbol for a resistor, it looks like that, or could look like this. Now, I think I think looking like that was done because I could do it easier in Word or something. I don't know. And a variable resistor looks like that. And my capacitor looks like that. Well, that also looks like some kind of a hydraulic actuator.
Yeah.
Yeah, I mean, who did that to me? My inductor's about the same. My battery's different. My fuse is different. My normally open, normally closed contacts are different. So we have to put up with the different symbolism. So I have an electrical thing. And I have that. And I have a plumbing thing. Plumbing thing. And I have that. All right, so in electrical thing, are the wires connected? In the plumbing thing, are the pipes connected? Okay, so connected. Connected, yes. No. Connected. Yes. No. Okay, so we're going to vote on it.
All right.
Okay. Electrical connection, how many is voting yes? Show of hands.
We'll vote yes.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we got 10 yes votes. How many no votes for the electrical guy? 1, 2, 3. Well, we'll throw you there anyway. Throw you under the
I
bus.
take mine back. I already voted yes.
I know you did.
I thought you were going for
You
the
went both
plumbing.
ways. Okay, now we're on the plumbing side. How many for yes? It's connected on the plumbing side. Yes. How many? No one? Yeah. Is this connected on the plumbing side? If I have something that looks like that.
It's not. The pipes are just crossed.
So I have 0 saying yes. I have 1. Someone's got it scratching his hand. There's 2. Okay. How many say no? It's not connected on the plumbing side. 1, 2, 3, 4, 5, 6, 7, 8, 9.
All right.
9 if I take the no scratch. All right. So now we're going to look at something else. And we're going to look at this. And we're going to look at this. Okay. Now, on the electrical side, is this connected?
Yes.
Yes.
On the plumbing side, is this connected?
No.
All right. So the correct answer here was no. We're not connected unless I put a no dot there. Okay, so the wires can cross all they want. They're insulated. They're not connected. There has to be a dot for the node. For the plumbing guy, those guys are connected unless I do something like that, saying that they're not connected.
I feel like an idiot.
Well, so what's new? For those that missed it, Jesse just claimed to be an idiot.
No, I feel like one.
Oh, he feels like an
Say I
idiot.
was
Yeah,
the idiot.
he feels like an idiot. But you made it to you made it to 25 years old, and you don't know if your pipes are connected. What can I say? But where in my generation, where did we learn that? In my generation, right? 8th grade shop class. Who taught the 8th grade shop class?
The local plumber.
A World War II veteran guy. Came out of World War II, took the GI Bill, was the shop instructor. 90% of what I know about electricity, I learned in 8th grade. Okay, where were those guys when you were in 8th grade, the World War II veterans teaching the shop classes? They had retired already, right?
Yeah.
Yeah, in general. So you got stuck with some 20-something math instructor female that didn't know how to plug in an iron, right? Teaching you you're now, and they don't even call it shop anymore. So, most of the high school shop classes, when those guys retired, that were the World War II veterans, the gear was thrown away and it was turned into an English classroom at most high schools. And that's really not good. I mean,
Yeah.
that's not good for us as an economy. It's not good for anything. But anyway, you have days like that. So things are connected, things are not connected. Push button switches. Oh, okay. On page 41, we have a rotary switch. multi-positional rotary switches.
Those are fun.
Okay? So it was so the mid-watch, before the ORS team comes in, Operation Reactor Safeguard Exam, comes down to your boat and makes sure you're safe to run the nuclear power plant. And ORS. And we go in and one of the things we do on the mid-watch before the team gets on board is we take their reactor controls, ABT, automatic bus transfer, in whatever position it's in. So if it's in port, then we move it over to starboard. Now why do we do that? We manually shift it to the other one. Well, we do that to make sure it works. And because if it doesn't work, we better fix it before they show up.
Aha.
No, that's the thing. All right, so the mid-watch does that, and pressurizer level, which is an indication, pressurizer level goes away. So I got, that's my normal indication. It's now pegged over here at 0. Loss of power. Now you have 3 different pressurizer levels. You have uncompensated port, uncompensated starboard, and compensated. All 3 are gone. Now this was 1981. This is 1981. Most of you guys weren't even born yet, right? 1981. And 3 Mile Island just happened the year before. And so pressurizer level is an important thing to know. The pressurizer is what keeps the core covered. So the core is at 480 degrees. The plant is pressurized at 1,600 pounds, and the pressurizer is about 1,800 degrees in order to do that. And so if you don't know what the level is, your core could be uncovered. If your core is uncovered, a meltdown could ensue. So it's not very fun. I'm the engineer, and I'm out of the bunk, and we're consulting the reactor plant manuals. And we get to the place where, okay, you have to go solid. Running the plant solid. So we're going to go solid. So now we're going to go and pressurize. We're going to add water to the plant, collapse the bubble in the pressurizer. So now the plant is solid. And at 1,600 pounds, we're safe, right? 3 hours later, we get to the point of the reactor plant manual where it says, oh, by the way, if you're solid, you can't be critical. Oh, okay, so that means we have to shut down the plant. Well, if we shut down the plant, that means our speed goes from our standard build we're at to zip, zap, nothing as we go on the emergency propulsion motor going 2 knots. So anyway, so we take the plant solid and we start going at the 2 knot rate. Well, we're supposed to pick up the ORS team at 6 o'clock in the morning. We end up picking them up at 3 p.m. And the only reason we get there by then is because the tender sent out 2 tugs to meet us, and when the tugs hook down to us, we can do 8 knots. Otherwise, we would not be there yet. All right. The ORS board walked on board. Now, what's the name of this? Is Operational Reactor Safeguard Examination. I'm shut down. We have no idea why we don't have pressurizer level. We haven't figured it out yet. We fail the ORS. They go away. They hit us on 3 major things. 1, we're shut down. 2, we haven't fixed the problem yet. And I forget what the 3rd one is. And the 3rd one was we replaced too much gear. We fixed too much. Well, when we were with the Commodore, I objected to that, and the Commodore agreed. How can you fix too much? That's the stupidest thing I've heard of. So 2 of the major things went away. We still got stuck with, 1 of them went away, we still got stuck with 2. We still failed, which means you have to redo it again. You can't go critical again until you pass now that you failed. Anyway, 2 days later, we find in the rotary switch, that's the compensated uncompensated level for the pressurizer, we find a fault in the switch. A piece of wire embedded in the plastic that has been there for 20 years without causing a problem, that caused a problem for whatever reason the day before my horse.
Wow.
I mean,
Talk about-
totally amazing. That one, that we could actually find the problem, and as soon as we found it, we replaced the switch and we got the level back. Everything was fine. But it just, one of those things that rotary switches also have the possibility of having flaws in them that will bite you in some part of your anatomy that will hurt really bad. All right. So now I'm on page. How far does chapter 2 go anyway? Anybody know? Goes forever.
Yeah, that's pretty far.
Yeah, pretty much
96,
forever.
I think.
96? All right, so we're not halfway through yet. All right, on the top of page 42 are dip switches.
102, actually.
Yeah.
102 and everything.
And a dip switch is a dual inline product. Dual inline package, right? And so it's many switches hooked in the same hunk of plastic thingy. Used for control purposes, they're not going to be used for sending power through. So it'd be good for 5 volts. If I'm going to send 120 volts through them, I'm going to have my head examined. Page 43, we have position switches. We use position switches all the time in my Coke machines. When I was a Coca-Cola repairman, I was constantly replacing them. One of the stupid Coke machine ideas came out that put a switch on the door. So when you put your money in, the can comes out, the door opens, the door swings shut, and then the cycle can start over again. Well, the problem is that the switch is right at the interface between hot and cold. The cold of the refrigeration going on and the hot of the outside. So it was always in a moist condition, and it failed often. Well, that was the first and last time anyone ever designed a Coke machine with a switch on the door. So if you go out there and look at the Pepsi machines in the hallway, there's no switch on that door that lets the product come out. If the product comes out or not, it doesn't care. It just keeps taking your money. But it was a good idea at the time, and it was guaranteed employment for me because I got to replace these switches that were pretty easily done.
So is there a code right you get for some?
No.
No?
No, afraid not.
Oh, yeah,
Page
no.
45, we see how mercury switches work. And we see that the switch moves over and the mercury moves around. Page 46 and 47, we have disconnects. So when you're doing your 3-phase wiring in the lab, the guy on top is a disconnect. All it does, it has fuses in it, yeah. Those fuses are 20 amps or 30 amps, but the purpose is to disconnect power or connect power, not to control power. Okay. Underneath, you have a motor controller. The motor controller is designed to turn the motor on and off. Okay. It's not a disconnect. So now we have, on page 47, we have pictures of disconnects that are fused and are unfused. So the ones that we have are triple hole, single throw disconnects. I drew my fuses wrong. I'm still got them wrong. Anyway, that's what they are. And on the first chapter test, you'll be asked to draw a picture of a disconnect.
Huh.
Yeah, really. Well, that's all right. We'll have a study guide, so we can practice
Okay.
doing it earlier. On page 48 and 49, we have a bunch of push buttons. And rotary switches and key lock switches and These things are a minimum of $50 a piece if all there are is just one lousy push button. When you add both normally open and normally closed contacts, that ups the price. When you go and add a key, that ups the price. When you add any actuator at all, a big mushroom, that takes the price and moves it up. These are all Rockwell, Allen Bradley stuff, is what all these guys are. And of course, there is also a new generation of switches that are safety switches. Okay, so if I have a regular switch, it's going to last for 6 million cycles. How long will a safety switch last for? It won't matter. If it fails properly. So a safety switch is something that is, and of course you get to pay a lot more money for it.
Oh, yeah.
But if it fails, it's going to fail to open the circuit. Okay, so my mushroom switch that I'm putting in there to be my emergency shutdown button, boom, I got it out. If it fails, it's going to open. Obviously, the ones we have are not safety ones. Okay, they're not going to do that. But for a mere $150, I can get a safety one. Someday I'll have the money. Who knows? Page 50, I show schematics of push buttons, normally closed, normally open. Okay, page 52, I show a bunch of other type of switches. And on 53, I have a drum switch. Okay, so this is a guy that goes forward and reverse on some DC motor. In this case, a three-phase motor. So that begs the issue. If I have phase A, B, C, and I have that hooked up to my motor, T1, T2, T3. I got that hooked up like that. Then if I do that, I'm going forward. Forward means clockwise. I'm rotating clockwise. How do I get the motor to go the other way?
Reverse through the wires.
Right. So if I go and hook A to T2 and B to T1, keep C hooked up to the same place, then I'm going to reverse the direction of the motor. I am? How is that supposed to work? All right, so I got my first phase is doing this. Well, that's really shitty, isn't it? So there's 360 degrees. So 60 times a second, it's doing that. My second phase starts 120 degrees away from the first one. That's something like, oh, that's gorgeous, just totally pretty. And then the next one's 240 degrees from the first one. Well, that's pretty close. So if I think of my motor as following these guys, I go from there to there to there to there. I'm going in one direction. But if this guy happens first, I've got to go that way, that way. If this guy happens first, I've got to go that way, that way, that way. First, second, third. And that's why I'd be going in a reverse direction. So that's a very simplistic way to look at it. Luckily, we have a whole chapter on which way the motor goes. But I'm showing on page 53, I take my switch and I move my switch and my drum switch, and I can hook up the three-phase motor to either be off or run forward or run reverse. On page 54, I have a 10-position binary coded decimal switch. Isn't that lovely? And of course I have those too. I don't think we wire them this semester, but next semester we get to wire them. So that'll be fun. On the top of page 54, I show foot-operated switches. So on top of 55, I show mechanical switches that have different actuators on them. Page 56, I show a bunch of different actuators. And so I have 2 different types of actuators in the lab. There are currently more than them. Limit switches on page 57. So there's whatever it is. The assembly line's moving down, my conveyor belt's moving down, I got a box on it. I only want the box to go so far. When I get there, I got a limit switch, stops it. I then remove the box. Page 58, I see that I can go and adjust my my on and off of my switches if I wanted to by a little bit. But I have some traveling position, I've got some force required, I've got all kinds of different things that I must do. Last time I was at the Ellison plant, they were doing a proof of process on an airplane frame. So you need to drill a hole to the airplane to put in your rivets, right? But if you put too much force, it's going to heat up too much, and if you don't put enough force, you're not going to make a hole. So they were having a robot with a sensor that was sensing the pressure on the drill bit, so it could do something that a human being is only doing now. You know, when you think about normal airplanes might have 100,000 holes in it. If you could go and do that with some robotic process over and over again, that could save some money, maybe. Some limit switches. Okay, we're at page 60. We've got to go to page 100. Why don't we work a couple homework problems? The early ones. Okay, like 1, 2, and 4. We'll try 1, 2, and 4 and see how we do. Problem number 1. Okay. Draw the solution. Draw the solution for example 2-2 using a double pole, double throw, single break, switch, contact configuration. Okay, so the first thing we have to do is find example 2-2, and because I've used this book in previous years, I happen to know it's on page 31 because I have it written in the cover there, 31. So go to 31.
31?
Yeah. Okay. Double pole, double throw. Okay, currently it's a double pole single throw. Alright, so we want to I want a double pole, double throw switch. Okay. Okay, so that's the switch. That's the switch I want to use. Double pole, double throw switch. Okay. Now I want to go and hook it up to the circuit that I have. All right, well, I'll put my battery there. 24 volts, 28 volts. 28 volts DC. And this guy, this guy I'll run to the red. And the other guy I'll run to Oh, I don't have a green one. Okay, so I don't need a green one, but I do need AC power. And the AC power will go to the motor. Now, why is it that I draw my motor looking so weird? Why don't I just draw a circle with an M in it for motor?
I guess the circle with the M means something else.
No, it stands for motor. You already have it in your lab. So when I go and I do this, that's a motor. When I do this, that's a motor. So why add? Yeah, why add? No. So this is showing an armature. Armature. And a stator. So the stator is a stationary thing. The armature is a thing that goes roundy. So that's what it's showing. But it doesn't have to show that. But the author's just trying to use more ink, I think. I think that's it. Well, that was good. Is that okay? Problem 2. Three types of DC motors are wired to a drum switch as shown below. Show how the motor windings are connected to the power for the forward and reverse positions of the switch. Okay, and this is page 53. So we're going to turn to page 53. This is going to take the rest of the hour just to draw the picture. All right, so there we go. Now here we have, on page 53, we have AC, and on this page we have DC. Okay. Now, somewhere in chapter 7 or 8, we talk about DC motors. And the DC motors could be shunt, or they could be series, or they could be compound. And right here we have those types of motors showing for us 4 chapters before we get to them. All right, so if I use the word shunt, what does that mean? That means, well,
have to use that word.
Okay, well, we won't use that word. When I use the word series, what does that mean?
Same line.
Yeah, so that means that the field winding and the armature winding is series. The field winding and the armature winding are in series with each other. Okay, well, if that's the case, then what would shunt mean? Well, shunt would mean they're not in series with each other. Right? So it means they're in parallel with each other. So shunt means the field winding and the armature winding are in parallel. So shunt means parallel. Series means series. What does compound mean?
Combo.
That means, so I would have a field winding, but then I'd have another field winding in series with the armature winding. So now that would be my loose definitions of shunt, series, and compound. All right, that being the case, I'm looking at something that has minus DC and plus DC. I got this switching, well, I will use this guy. I have this switching case sitting here. And I got 1, 2, 3, 4, 5, 6. Alright, so I have something that looks like that. And I see that 2 is hooked up here to negative and comes over to my field winding, F1, and that is connected to 5 and 3, so it's going to come over here to 5 and 3, F2, field 2, and then, here's that guy. Then we're going to have positive coming into 6, and then we're going to have the 4 guy going into the armature, A1, and then out the armature A2 into 1. Alright, so now I've done that. I draw exactly what is already there. So show how the motor windings are connected to power for the forward and reverse positions. Okay, so do I have enough colors left over? Okay, so I'll go green. So green is forward. So how are we going to be hooked up going forward? And it says 1 is connected to 3, 2 is connected to 4, and 5 is connected to 6. Okay, so that's what it says on the top of page 53. And now I see I come in, and my field winding is in parallel. Let's see, this is shunt, right? So this is supposed to be, well, this is supposed to be shunt. So I'm supposed to be both of them. And yeah, they are. So the field winding and the armature winding are both in parallel. So I'm negative to F1, negative to A1, positive to F2, positive to A2. Okay, so that's fine. Now I put it in reverse. So I'm gonna put it in reverse. I'm gonna be connected that way, that way, that way. Alright. And that's what it says. That way, that way, that way. Now, that reverse, that means I'm in parallel, so F1 and A2 should be connected. So F1 is connected and A2 is connected. Okay, and F2 and A1 should be connected. Okay, there's F2, there's A1. Okay, so now I did it right. Now, yeah, what we'll do is we'll do a, this is shunt. What we'll do is I'll copy this over and erase the green guys. So that'll be my plan. Copy. Paste. And I'm gonna erase the green wire. Erase the green wire. Erase the green wire. Okay, so I have F1 connected to A2, and I have negative connected to F2 and A1, and so this is going to be my reverse shunt. Oh, that's just so lovely done. Yeah. Now we have 2 more to go, each of them requiring 2 parts, right? So that means I have 4 more pictures to do. Oh, let's see. I guess I just should start over, right? That'd be the best thing to do. So we're going to look at series. Okay, so I got my enclosure. I got 1, 2, 3, 4, 5, 6. Now, when you hooked up those that hooked up their AC motor to 3-phase power and did it right, the motor showed you where to hook it up to, right? Well, the same thing's going to happen on a DC motor. A DC motor is going to tell you what to hook up to where. So, and I don't have any DC motors to hook up, so it becomes an exercise. All right, so here we go. I got my armature winding A2, A1, and it's hooked up to 1 and 4. 1 and 4. And then I got my field winding. Now, why are they calling the field winding S1? I don't know. Probably because it's in series. And it's hooked up to 3 and 5. 3 and 5. And then I've got a plus guy going into 6. And I've got a negative guy coming out of 2. All right. And because I know I'm going to need this guy twice, I'm going to make a copy of him before I draw in him. And that'll make life slightly better. All right, so now I'm looking at going forward. F, W, D. So I'm going to go forward. What color should I use? Blue. Okay, so my forward switch says these guys should be hooked together, those guys should be hooked together, and those guys should be hooked together. So in series, I'm going positive to S2, out S1, into A2, into A1, and out to the negative guy. So I've got, I am in series. I'm going in A2, out S1, in, out, in, whatever. So I got the right path. All right. So that's the forward direction. Now I'm going to look at the reverse direction. Reverse direction says I have to hook up that guy, and this guy. So I come into S2, but then I go S1 to A1, and then I go A1 back out. So I've switched the polarity of the armature, making me go in reverse. Okay. How wonderful is that? Okay, one more set of pictures. And this is for my compound guy, compound motor.
Can you go back to that one?
Okay, moving back one.
That one, thank you.
So I'm going forward. I go positive into S2, out of S1, into A2, into A1. So I've got reverse. I go positive into A2, out A1, into A1, out A2. So if I go S2, A1, S1, A2, A1, I'm going forward. And if I go S2, S1, A1, A2, then I'm going reverse. So I reverse the armature windings. When I reverse the armature windings, I go the other way. And same thing happened when I was in parallel. So when I was in parallel, F2, F1, A2, A1, I'm going forward. And when I switch them, oh, that's good. I'm putting the squares where I should have the circles, and the circles where F2, F1, A1, A2. Then I'm going reverse. Okay. So now we're going to draw another picture for the compound motor. One, two, 3, 4, 5, 6. Now, the most complicated, in 17 years, we've had to hook up 2 motors that were more complicated than what we have in the lab. One of them is a 5 horsepower motor that the carpenter guys have, the construction trades people have. They have a 5 horsepower motor on their table saw. And it turns out that due to the configuration of motors, you would want to start a motor in Y configuration and then have it run in delta for your most efficiency. So you have 12 different wires, and you wire it so that it starts Y, runs delta. And that doesn't make any sense to you, but it will before the end of the class. The other guy we had is a 10 horsepower motor in the welding lab that that was having a problem. It was the exhaust fan, and when it turned on, it would take a suction in Dodge Hall, and you couldn't open a door to get in. Okay, well, that was good for the welding guys, but obviously we had to do something about that. So what we did is we made a control circuit for the welding guy, and when you turn the on button on, there was a 2-minute delay waiting for the damper to open out to open up to the outside, so that we wouldn't draw a vacuum on the building. And then when this guy turned on, it would move 18 inches in the overhead. It had 4 rods that were 1/4-inch rods. Oh, maybe they're 1/2-inch rods. Probably 1/2-inch rods. But it moved 18 inches in the overhead. It had a great big boot that allowed it to do that. I mean, so it was designed to do it. But every time it did it, concrete things, dusted down from the overhead. And when I'm looking at it, I'm saying, it's not going to do that for another 5 years before it falls out of the ceiling, and the thing's going to break. So we put a variable speed controller on. We had a 2-minute delay opening the damper, and then we took 2 full minutes for it to come up to speed, variable frequency, and 2 full minutes for it to turn off, coming down. And when you do that, it doesn't move in the overhead. There's no perception that it's moving at all. It's really cool. So those are the 2 more difficult things that we've done. But this compound motor is pretty cool. All right, what page am I on? I have to goofed off enough. All right, so I have a field winding, F1 and F2. F1, F2. And it's hooked up to 2. And it's hooked up to 5. And then I've got a series winding that's part of the field, and it's connected down there, S2, S1, and S1's going to go to 3. And then I've got the armature winding, A2, A1, A2, A1. It's going to go to 2, and it's going to go to 4. Okay. Copy. Now, when we do a test, remember to bring in your crayons. Otherwise, you won't be able to do the, huh? What? Yeah, bring in your crayons. Why not? So, we're going to go forward. Okay, so that's what we're going to do first. We're going to do it in blue. We're going to go back to page 53. And forward says, these two are connected, those two are connected, and those guys are connected down there. Now, I left something out. What did I leave out? I left out plus going to 6 and the negative going to 2. Okay. And what we'll do is we'll move this guy down. And now we got some room here. So now we're gonna follow the plus guy. So the plus guy is coming around to F2 and S2. Okay, and we're going to go that way, and then F1 is going to go to negative. So F1 is going to negative. S1 is going to A2. So S1 is hooked up to A2, which is hooked up to A1, which goes back to negative. So that's how I'm hooking up my compound motor to go forward. To go reverse, I'm just going to switch around my A1 and my A2. Okay, so now this guy is my reverse guy. Again, I managed to leave out the plus, and I left out the minus, so I'll put them in wrong color. Minus. Okay, that looks good. What is the color coding of a common DC wire?
Blue.
White with a blue stripe. Do I own any white with a blue stripe wire? No, I don't. So you'd use white in our applications. DC, positive side of DC is going to be blue. All right, so where are we? We're going reverse. So I'm going to hook up him to him, them to them, them to them. Okay, so that's reverse. And I'm going to draw a picture of it. I'm going to go positive to F2, positive to S2, F2 back to negative. S2 goes to S1. Okay, so S1 goes to A1. Goes to the motor, goes to A2, goes back to negative. Yes, it does. And so that's how I go. I get it to go in reverse by switching the armature windings from one side to the other. Okay, with that, I guess it's time to go to lunch.
Which of the field wire?